Okay, this video is to support your reading of section 8.2.1. Okay, the idea here is that the chemical potential, which we found last time, we're going to apply it to the case of a chemical conversion, a chemical reaction where one molecule turns into another. So to do so, we're going to assume there's these two molecules. They can interconvert 1 to 2 or 2 to 1. And we'll just assume, for clarity's sake, that the internal energy of molecule 2 is greater than the internal energy of molecule 1. Now, a conversion from 2 to 1 is straightforward. We don't even need to think about entropy because that would be using up energy to create energy 1. That would be an exothermic reaction. It would give off thermal energy, and that's fine. We're comfortable with that. But a molecule converting from 1 to 2 would require to take energy to create this internal energy, which seems to defy our understanding of energy, yet we're going to see that it would be favorable because of the entropy rise. So it would be an entropic interaction. Okay, so let's go ahead and move forward. We'll assume that the reservoir, the environment, as well as these molecules are all contained so that the total energy of the system is conserved or constant. So our thought is we want to find what the change in entropy would be right here. What is going to be the change in the total entropy of this combined system when we convert one molecule to another? So to do so, we need to say, okay, well, how would it change when we convert one molecule times how many of those molecules we make, which will be just one in this case, okay? And then do the same thing for molecule 2. Now, the thing that's important here is this derivative of how the change in entropy as you change one molecule, okay, or change this type of molecule, we already know what that is. That is negative the chemical potential over the temperature. Okay, and the same thing will go for this case for species number 2, the second type of molecule. Now, in this particular case, we're going to focus on one molecule change. That means we'll say 1 went to 2, so type 1 changed into type 2. So that means we lost one molecule of type 1. So delta N1 is -1, and it turned into delta N2, or so delta N2 itself, or it turned into type 2, so delta N2 is +1. So this is +1, this is -1. Okay, so they kind of offset these minus signs, and so we end up with this change in entropy equaling the difference in the chemical potentials divided by the temperature. Okay, so now we need to interpret what that means for the total entropy to increase in order to allow for a spontaneous conversion of type 1 to type 2. Okay, so an increase in potential or entropy means mu1 must be bigger than mu2, or that difference we saw has to be greater than 0. So what is that difference? Well, here we use our definitions of the chemical potential we found earlier. Okay, remember that it is a term, an energetic term, that is dependent on the concentration over some reference concentration, which is often taken to be 1, okay, as well as the internal energy, and then the other stuff. There was all that other stuff, but that was independent of the type of molecule. It didn't matter. Okay, it was a function of temperature, but other than that, it didn't matter. So they both have the same form, including that same constant. So subtracting the two, that constant disappears, and we end up with this relationship using the rule of natural logs. Natural log of A minus the natural log of B is the natural log of A of the quantity A over B. So we get C1 over C2. The C0 is canceled out. All right? And then we have the difference in energy. So now, as we look at this condition, that the difference must be greater than 0 for it to be spontaneous, we can see what that means. In order for this to be true, we've chosen that E2 minus E1 is 0 because E2 is greater than, E2 minus epsilon 2 minus epsilon 1 is greater than 0 because this was the larger value. So for our particular case. So in order for this to be spontaneous and this whole thing to be greater than 0, that means this first term that's dependent on the concentrations must be bigger than this difference. And that is the entropic change. Okay? So the concentration of 1 needs to be sufficiently larger than the concentration of 2 so that this term is larger than the energy difference. Now you think, okay, well, that's starting to make sense, because if I have a whole bunch of C1, then even thermal fluctuations should cause it to switch over to C2. But you can also think of it in terms of order. If we have a lot more of C1 than we have C2, that's a big difference, and that's a big organization. There's order to that difference. If these are much closer to each other, there's less order in that. And making C1 lower and C2 higher would mean a lowering of order. So this would be spontaneous in the sense that we have used up some order. That has increased our entropy by making these concentrations closer to the same value. Now, let's just step back just a bit to make it a little more general. If our energies were the other way, then this could have happened even if these concentrations, if C1 was less than C2 or not big enough, because then energy will do the job. Okay, we can have energy be sufficiently, we use up some of the energy to convert, and that's good enough. We're comfortable with that idea. Okay, so let's take this now to think about all possibilities. So before, everything we did, we considered a change in entropy, assuming the energy is constant. Also, we didn't explicitly state it, but we assumed the volume was constant. But what does it mean if we let anything change? We let energy be exchanged, we let the volume change, and as well as the numbers. So following a similar pattern as we did before, if we want to find out the change in entropy of the system when everything can change, well, we change one thing, holding the others constant. In this case, it actually has a factor of dn1, but we'll just let that be 1 in this case. This also has a factor of dn2, which would be -1 in this case, for this general example. It's not necessarily the same as before. It's just a general example. Okay, but holding the energy and volume constant. And then here we have a change in volume. So how does it change when you change the volume, holding energy and the numbers constant, times how big of a change in volume did we make? So this is kind of like a slope, a point slope equation. And similarly for energy. Okay, but each one of these derivatives we know something about. Okay, these two we've already seen. That's negative mu1 over t, negative mu2 over t, but we already have a minus sign, so that becomes positive. Now, we haven't seen this since chapter 6, but ds over dv is actually the pressure over the temperature. Okay, and similarly, this ds over dE, that was our first derivative we looked at. That's equal to 1 over the temperature. And so plugging all those in, and then multiplying out the t, so we get t delta s on that side, and grouping it just this way, we have our chemical potential contribution, we have our mechanical work done by expanding or contracting, and then we have our change in energy. This could be internal energies or some other potential energy and kinetic energy. So that makes it like, well, TDS, that's inside free energy. So let's talk about the Gibbs free energy, which includes all those things. Well, Gibbs free energy is delta E plus P delta V minus T delta S. Okay? But if T delta S, put a minus sign here, which kills that minus sign, makes these two minus, that means these two terms cancel with these two terms, and we're just left with this. And we're back to where we were before. And so even if we allow all things to change, not just numbers of particles to change, we can correctly describe the spontaneity of something by looking at just the difference in chemical potentials. Okay? So it's just the difference in chemical potentials. Now, I will point out in this case, here we have mu1 minus mu2. Now in our previous example, okay, the previous example, we had 1 being converted into 2. So 1 was a product and 2 was a reactant. Okay, but I also had this, the values here were switched a bit. So this was a +1 here and a -1 here. So that's, if we reverse the minus signs here, we have what we had before, and we see it's exactly the same. where would be the positive of the products minus the reactants. And that's going to lead us into our discussion of the mass action rule in the next subsection.